Hey everyone, today I'm going to be doing a Div1 contest. This is Codeforces round 684. So it's going to start in about 30 seconds. Let me start doing like final, let me start getting my pages ready to load. This is kind of interesting. The first problem apparently will have subtasks, and the last two problems will have equal weight. So we will see how it goes. Good luck, everyone. My Chrome crashed. Well, okay, so Okay, yeah, we'll just copy paste. So find either a clique of size k or a set of non-empty vertices, non-empty subset such that every vertex has at least k neighbors in this subset. So I mean, really, you should just take away the guy of min degree, right? Like, anyone who has degree less than k is k minus 1 is obviously, like, useless, right? If there are no required subsets or cliques, print -1. So if this guy is connected to less than k people, then obviously we should just delete him. Otherwise, yeah, so the latter is easy to check for. Okay, so Okay, so if like, yeah, so like k has to be pretty small. Like k has to be O of n at most. I don't really want to have to traverse all the edges that often, so that's going to be a bit of a problem. But yeah, let me think about it. So what happens is that you okay, so first of all, like, all of these guys eventually get removed, right? Like the subset does not exist. So if the subset does not exist, that means that so first of all, we'll peel away anyone who has size strictly less than k minus 1, who has degree less than k minus 1. So everyone here has degree at least k minus 1, and then when you remove things of degree k minus 1, they kind of pull other guys off. They pull other guys out. This guy creates at least one other guy of degree k minus 1, then this guy, like, and this guy, and then this guy, and then so on. And so if you consider where this guy is in the clique, what this clique does, like if there is a clique, if there's no clique, then you could still just pull people. Well, if there is a clique, it might be a while until it gets pulled off because of, like, yeah, because of this. So but at least I'll start writing this. Okay. So these are everyone who's alive. I'll just say Okay, so then, now what do? We take all the k minus 1s, and we delete them. Total number of vertices here is at most m over, everyone has, yeah, the total number of vertices is at most m over k already, right? For each vertex, you don't really want to run O of k squared time. So let's just assume that this thing's empty, then consider so this guy's empty, which means that there is no subset such that everyone is connected to. At least. So this guy minus this guy subtracts 1. This guy is linked to some subset down here. This guy is linked to yeah, so this is linked to somewhere in this subset, somewhere in this subset. If there's a clique, okay, if everything gets eliminated, then this thing must be like, I pretty much just want to be able to like check this, but it is a little bit slow. I mean, n root n isn't too bad. Okay. if the location, when you find j, if it's equal to the end, then go to bad. This is n squared root n. Should pass without a problem, I think. But, oof, wrong answer? That's no good. Okay, let's see. Why would it be wrong answer? Oops. This should be, yeah. should be k-2 because I already subtracted off the degree connected to yourself. Alright, maybe I should have read C first. It looks like C was not hard. Shops are numbered 1 through n. Set max. He visits. Okay. Okay, so Q, read in N and Q. So the costs of the meals. Yeah, I guess we will just the array is non-increasing. So for each shop, set AI equals max AIY from 1 through X, which means that the first X shops get increased. And so it always stays non-increasing. Which means this is just range set. And then this is, like, is the point of this that I'm not supposed to do log squared? Because otherwise it doesn't seem very difficult. Like, this is not that large a bound. Yeah, like, do they just want me to binary search? Guess I can do it. Oh my god. Alright, yeah, this is actually, wait, so you can buy at most square root n distinct items, right? Or like 10 to the 4 distinct items. Square root y distinct items. Just 10 to the like 3, 4. The number of intervals that he does buy is like pretty small. Like, if you, like, eventually you get blocked, and then like the amount of money you have has to be less than this thing, right? And so if you can buy one thing, if you can buy one more thing, then like if I can't buy one more thing and then I can't buy one thing, this means that my the amount of money I have like at least halved, right? So yeah, I think this is the right approach. So n to m to the, yeah. Interesting. So, yeah, okay, some in ways. So what we can do is we can casework on where the first person goes. Yeah, we can casework on where the last person sits. And oh, n is small. Okay, well then it's it's this polynomial. Yeah. 4 is not so bad. What is m? Yeah, so it's so the DP is in an array of size n. Yeah, I guess it's just like yeah, okay, so we can just take the case for it. This thing is entirely filled. Like this thing is yeah, this DP is easy. So what's the DP for an array that's entirely filled? Well, it is like you can either, if someone sits here, then if this is the last person who's down, then oh, no one can cross this line, right? Yeah, no one can cross this, which means that this is just yeah. Okay, so Brief whiz. So this and this equals 0, which means that it this is like this fractal thing where yeah, this is like this fractal thing where it's like this and then you copy it over here and here. Okay. Yeah, each operation is either plus x plus 1 or y plus 1. It's an ID. Some good cells are black, others are white. Each player on his turn chooses a good cell and a subset of ancestors and reverts their colors. And flips all their colors. Yeah, okay. So Yeah, so this is just like essentially just putting an extra token here. Initially, all cells are white. You're given n pairs of cells for each pair. Wants to win and decide to cheat. Okay, so let's just analyze this problem. So subset of its ancestors and reverts their colors. So any node has, you take the max of this subspace. Like you can take subset of its ancestors. So you always flip this guy, and then you can go to, so yeah, you can go to any of these states. So this guy is, yeah, let's just start drawing. Let's just start drawing. We can definitely finish this round. So the grid looks like you have this thing, and then you have this thing copied a second time, and then you have okay, so first of all, this tree is not quite symmetric because any given point, like, yeah, okay, yeah, so it's, oops, that's in the wrong place. Okay, so this is 1, 0, this guy is 1, this guy, wait, don't you just care about depth? So, yeah, you only care about depth, right? So the hard part here is just the tree part. Right. Okay, so it's, yeah. Exactly what? Yeah, so we just decompose it into these things. This guy, I guess, is just special, and then everything else is like, everything else is determined by either this thing or this thing. And then yeah, you just interval union it together and then call it a day, right? Okay. Yeah. So the deeper of the two has to. Which direction stays? GG's. I guess I should spend some time looking for hacks, because definitely could be some hacks. Interesting. This n cubed is like a little bit slow still. Because it's like n cubed mods, right? Yeah, this Waze is... Let me just make sure that this D... Just make sure that, what's the run? It's, maybe I should use the barrel reduction and stuff, but we'll just try it. So 500, 500, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I think this will be fine. Like the access this is the runtime of this thing is pretty much independent of the input bounds. So like this thing should be significantly faster. Yeah, it should be pretty much linear in the input. Like I guess quadratic in the input side. So we can try some like strange numbers to see if like it changes drastically, but it doesn't seem to change much. So I think I'm fine here. I think this is pretty much like the fixed upper bound. Yeah, I actually suspect that it's, in this case, it might not be the array accesses might actually be kind of fast, be fast enough. It might just be the what's it called? It might just be the data being the mod being slow. So in theory, I really should have used like a barrel reduction thing, but I don't have that code on hand. So yeah, I think I'm gonna get passed by Omnic, or I could definitely get passed by any number of people if they solve this problem. How many points is this worth right now? 12. So I could get passed by like any of the top 5 people right now. So they have like 10 minutes. Yeah. I think all of these changes were just, they screwed up their LaTeX and they like left a lot of dollar signs in there or something. So that was kind of silly. But yeah, there's not much I can do on this front anymore. I guess the question is, do I resubmit D or not? I don't think I'd bother. And then E is plenty fast. E is kind of data dependent, but it should be log time, and like it should just use these things, so I'm not too concerned about that. Here the has root thing is like yeah, this has root flip is correct now. it should be from -1 to 0, and then you exclude -1. So we'll just like exclude it right here, and then we don't have to deal with that later. And yeah, I'm not really concerned about integer overflow here. Like all these integers are like, yeah, everything should be in range. The depths are at most 2e9, and the I don't actually subtract any depths. I just compare them, so that doesn't even matter. Like as long as the numbers are small, enough, then everything is fine. And yeah, everything here should be fine. Okay. TLE. Oh wow, they're getting TLE. That is not. And so my thing was definitely just a small bug. Like I just had an off by 1 somewhere, but I guess they actually had TLE. All right, time to go look at this room. I don't think anyone has any hacks yet, so might not be any hacks. Another thing I can look at is sometimes the authors write strong pretests in their thing, and these guys did not say anything. So we can let me just open these up really quickly and just make sure I know what's going on. Yeah, N and M are at least 2. Graph subset problem. I don't know. It's not really possible to hack that either. Yeah, okay. So let us. Yeah, not. Yeah, let's lock these problems. I actually don't even know how the hell you would C seems like a really hard problem, so I don't really know how people manage to. Man, I really don't want to read these people's code. Also, everyone else has a. It's only 110 now. Yeah, so I think. Yeah, Omnic still has a chance to pass me. So people still have chances to pass me, but now that they have Ron Submits, it's like a lot tougher. It gets tougher. What am I even looking for? Integer overflow in C? I don't even know. Yeah, I'm not even sure what I'm looking for. Now I really shouldn't resubmit D, right? Because yeah, that would just kill my win. Yeah. Okay. What am I even looking for? Yeah, I don't know. This problem was so strange. I'm not actually... I feel like they could have done more with this problem. Like, the fact that you just like straight up just like... I thought the game part would be more interesting, but really it's not. It's really just this tree problem where you like, you know, you need to count the number of things that are set on the tree and stuff. Like, the game is just... It's just constant number at a constant... Like, the number is just the depth, which is very, strange. There's no way that this thing is wrong, like it, unless it integer overflows, but a and a+1 are... Wow, I'm surprised it takes so long. But yeah, it shouldn't be any integer overflow. Yeah, so I should really look for a hack. And kind of just make sure that no one else has. All of this code is so ugly though. Also, hacking is really dangerous. Like, I don't know. I really shouldn't, but I am usually pretty reluctant to hack. I really don't understand why D was so hard. C was definitely like a tougher data structures problem, I feel. But yeah, I guess I just pulled through and solved D and E fast enough. Yeah. Interesting that people are TLEing. Okay. Is B easier to hack? Nick is slowly, well, he still has 50 seconds. We'll see if he passes, but I think at this point, like, I'm not gonna hack, and we'll just see. Oh man, yeah, okay. Nick is slowly bleeding out his submissions. He definitely might, if he passes, I'm not really sure. He's at minus. Yeah, if he passes his next submit, it's still fine for him. But I don't know. It's tough to fix bugs in the last second. So yeah. Well, that's that. Let's see if Nick made a last minute submit or not. He did not. Yeah, let's see. There's some final people running on pretests and stuff. But yeah, that was a good contest for me. Let's hope I don't fail any of the. Let's hope I don't fail any of these problems, particularly D. But I think when I was doing the testing, like, all the runtime is pretty consistent, so that is looking pretty good. I actually felt like C was by far the hardest problem on this set, on this problem set. Like, C was this non-trivial, like, binary search on segtree thing, which is not something that you typically code. But I guess, you know, I mean, I think the timestamps of my submissions roughly back that up. Like, C actually took like 35 minutes. E took, I guess, like about the same amount of time, like 32 minutes. D took like 15 minutes. So yeah, it felt like C was really the hardest problem. But I guess I don't know. I guess it wasn't quite. I guess the authors didn't feel the same way. But yeah, that is a good game. We'll see the. I won't film waiting for the standings. Who knows how long that'll take. But good games. If any of you guys have questions about, if any of you guys wanted to see like more details about the solutions, I think the best place to look is probably the editorial. The editorial write-up will be better than any explanation I can put together right now. But I can go over a quick overview, just, you know, since people sometimes are curious. So problem A is about you're given a grid of zeros and ones, and you can take any 3 cells in a you can flip any 3 cells into a 2x2 square. So really what that means is you can flip like this little L shape inside any 3x3 square, and your goal is to change the entire grid to zeros. And so in the first one, you're allowed to use 3 NM moves. And one thing you can do is there's actually a simple way to flip one cell, which is consider any 2x2 cell that encloses it. You just flip all 3. If you flip all 3 that don't include this, if you flip all 3 L's that include this cell, so like this one, and this one, then this cell actually flips. And actually, if you flip all 4, then the entire cell flips. But that's not so important. So what happens is you can flip any given cell in 3 moves, and so you just go through and apply these 3 moves for every cell that's currently a 1, and that works out. In the second version of the problem, you only have NM moves, and so it's really not that more complex. One thing to observe is that if you apply the same flip twice, it cancels out, right? So to solve a 2x2 square, there are only 4 possible flips. So you can definitely solve a 2x2 square in at most 4 moves, right? To solve a bigger rectangle, what you can do is you can slowly eliminate rows. So if you look at the bottom row, if there's a 1 at this cell, you just like flip this little L that contains this 1 and nothing else, and then you like do this for everything in the bottom row, and you eliminate the entire bottom row. So eventually you get to a 2x(n) strip, and then you can also do something where you like eliminate from the end of the strip. And so this gives you like, actually gives you like O of n minus 1 times n minus 1 or something flips, and it's pretty, yeah, which, you know, all works out. Problem B I also thought was kind of tricky. I don't really have a great solution. So my solution is, so first of all, any node that has degree at most k minus 2 is totally useless, because everything in the clique has to have degree k minus 1, and everything outside of it has to have degree k, right? Everything in the subset has to have degree k. And so if you you can just remove every vertex that has degree at most k minus 2, and like that'll remove some edges, and then so that might decrease some other vertices degrees, and then you can, you know, recursively remove or iteratively remove everything that has degree at most k minus 2, and like keep going. So eventually you're left with this graph that such that everything has degree k minus 1. So one thing you can do is you can remove, if you're trying to find a subset, you can just remove all vertices that have degree k minus 1 and like iterate again, and eventually you're either left with all vertices that have degree at least k, in which case you know, this set is a good subset, or you run out of vertices, in which case there is no such subset. So the subset is really easy to find. The clique is trickier, but I think what you can do is, like, when you remove a vertex, it has to have a degree k minus 1. You can just when you remove a vertex of degree k minus 1, you can just delete, you can just check all its neighbors. And because all vertices here have degree k minus 1, and the number of edges is only like 10 to the 5, there are most m over k different edges, right? And pretty much it just means that k is only like square root n or something, or square root m. Because k is only square root m, like if you naively check the clique size, I think this only takes like O of m times k, so which is like m root m. So this is like a square root n time solution, and it should all work out. C is like a tricky problem. C is I thought C was by far C was the trickiest problem in this set, I think. But pretty much you're given an array of integers. It's decreasing, weakly decreasing. And at any point, what you can do is you can take a prefix and you can say, set everything in this prefix to at least k. So that might increase something near the end of the prefix, and some things near the start of the prefix might not change. The other thing you can do is you can say, this person starts here, starts at this shop, buys some number of things, and then like moves, buys some number of things. He goes through all the shops, and if he has enough money to buy something from this shop, he buys something, and otherwise he doesn't. Otherwise he just moves on to the next shop. And the question is, like, how many things does he buy? So what we do is we just maintain a segment tree of like a lazy like range set segment tree, and the first type of operation always just sets a interval to y, because because the prefix is the stuff that's bigger, that's originally bigger, and then there's like some stuff that's equal, and then the stuff afterwards like remains small. So you do that. And then for the second type of operation, it's kind of tricky because like he could like eat here and then run out of money here and then, you know, eat somewhere later down the road. And so those aren't contiguous intervals anymore. And like segment tree analysis is all about like contiguous intervals having only log n parts. So that's no good. But what you can realize is if he's able to eat here, if he can't eat at this location and then can eat at a later location, and then he can't eat again, that means the amount of money he had must be less than the amount that he paid to eat, right? And if the money that he has left is less than the amount that he paid to eat, then it at least halved, because later shops are cheaper. If he can't eat at a later shop but ate at an earlier shop, then he must have less than the earlier shop as well. So the amount of money must have halved, and so it can have at most log n times. And so if you just kind of implement the algorithm, you'll realize that it really only uses like the places that he eats at form log n different intervals, and so you can do this binary search on segment tree thing to finish that up. One thing to note is that so as long as you like are efficient about the binary search on segment tree, then everything just works out. One interesting thing is that there's this weird thing about he starts at the X shop and goes rightwards. And so you can deal with that explicitly in a segment tree. That's not too hard. But another way you can deal with it is you can just say, we'll just give him enough money to eat at the first X-1 shops. So we'll just compute that sum, give him that much money, and then he'll obviously eat at the first X-1 shops, and so we can just subtract that off from the final answer. So that's a like little trick to save you a little code. Problem D was really just a DP. The key insight is you just look at where the last person sits. The last person has to sit. So first of all, like let's just like take the range and divide it into intervals of like places where people sit and then places where no one sits. If no one sits at a given location, then like it doesn't. We can just delete it without any problem because like no one will ever cross that cell. So the key insight is that if no one is sitting at this cell, then like no one can cross this. So we can essentially just split that array into two pieces. So first, the one thing we do is we're only going to solve the case where like the entire interval is eventually filled. And if the entire interval is eventually filled, what you can do is you can casework on where the last person actually sits. The last person could have like had their target be anywhere to the left of it and moving right, anywhere to the right of it and moving left, or like at this location and moving either left or right. And also right before the last person sits down, these two intervals like are the people to his left and the people to his right are separated because of are separated by him, and no one can cross that interval. So then you can like do this DP downwards, and so it really is just this combinatorial DP. Mine is n cubed time. You might be able to get n squared, but I didn't really think that hard about it. My code actually took a long time to run because I guess there are n cubed mod operations, and mod is like a rather expensive operation. So that was definitely like a little bit bad. One thing you can do is you can use like Barrett reductions or things like that, which like are a more efficient. For a fixed mod, you can do some pre-computation, which makes it so you can take mod that number very quickly. And so we could have done that, but we didn't. So yeah, that could have sped it up. And eventually I might put that in my template code too. But for now, it will just barely fit in time. The last one is this problem E, cheat, and win. This problem is about this like two-player game. On like this tree, they give you this tree. There's this two-player game on the tree where like some nodes are black and you can like flip things. And they give you some paths on the tree to mark as black, and then you're asked to say something about how you can win. I won't talk too much about the details. I think the editorial probably does a good job of describing it, but I'll talk about two things. The first thing is this common trick. When you see a game where this is kind of this there's this nice general like statement about impartial games. which is that if there is a or like sums of impartial games. So if you have it's pretty much like a game plus a game equals like a game plus a game. If I'm going to assume that you guys know what the sum of a game, two impartial games are, but the sum game of like a plus b equals a, right? So if you have b plus b, it's equivalent to 0. And that's kind of interesting here. Here what we're trying to do is we're trying to say like you're flipping colors, right? And black means that you kind of like can play a move here. So if we think of black as like there is a token here, and then white as like there isn't a token, what we're able to do is we're able to take a black cell and flip some subset of the ancestors, i.e. change black to white and white to black, right? But another way of viewing this is instead of just flipping them from white to black, we can say from white to black is like adding a token here, and from black to white is also adding a possible move here. And then like essentially like if this cell is black twice, it's equivalent to white because like the two games cancel out, because that's how impartial games sum together. So actually one way you can phrase this is there's this tree, you have a token at some number of nodes, and then for each node you initially have one token on each black node. When on your move, you can take a token from a black node and put a token on some subset of its ancestors, and a token, a game like a cell in the original game is considered black if it has an odd number of these tokens. Alternatively, like if you have two tokens in this new game, then they cancel out because they're like the sum of an impartial game. They're like each token represents like its own impartial game that is summed together, and so like they cancel out if there are two of them. So really, what this is on your turn you can take a black cell, you can take a token, you can remove that token, and add tokens to any subset of its ancestors. And this is like a very common trick that you'll sometimes see, and like it's pretty surprising if you. Or maybe not surprising. It's pretty it's really like a different way of thinking about like these sums, or like this XOR thing. It's just like a neat way of encoding XOR into these sum games. So if you see this game where like you can take one thing and then flip a bunch of other things, instead of thinking as flipping, think of it as like adding a token to each of the other things, and then like those will be legal moves. Because flipping is exactly the same thing. Like one way of putting it is like numbers have characteristic too. So like when a plus a equals 0, and that's exactly what flipping is. So the second thing is that we're essentially trying to take this like we're essentially trying to take these paths and decompose them into like short intervals, and that's not too hard either. That is really just like this one way of thinking about it is like heavy light or something, but really what you do is you like for each node you consider like this is kind of like heavy light. For each node you consider like a good path that goes from it to like some other node, and then this good path is this good path must have the sorry, what was I saying? Yeah, so this good path must end at this node. Oh, is my code gonna fail? Huh. Because I needed to... Oh no, my code might fail. That'd be really bad. I might not have included enough things in my hash map when I'm computing these roots. That'd be really bad. Yeah, I think my code is gonna fail. That's really bad. I don't know why I didn't realize that, but I really should have just put like this entire location into the cell. Uh-oh. That's really bad. Yeah, I think my E is gonna fail. It's surprising that it passed pretests. But yeah, I don't think I included enough data. So pretty much you need to take these paths and deduplicate them. That's the hard part of this problem. And so the deduplication is just the code that you have to run. and then you just collect them. Like the numbers are easy to compute. The number of a cell at depth d is just 2 to the d. So you're just trying to compute the number of which depths have an odd parity. And so the hard part is just deduplicating these paths. But yeah, I think my code is gonna fail, which is really bad. I think I should have just done like u in 64t. It's really surprising that I passed pretests, but I guess sometimes pretests are just weak. That's now I'm really nervous. I guess we will just, you know, wait until systests are done on stream because we have some time. But yeah, that would be really embarrassing if I managed to fail systests on. Well, like, I don't know if it would be really embarrassing, but it would be, like, just not very good if I failed systests like this. I actually think you don't need D because, like, D is always the opposite direction as you're going. You actually do want D, never mind. Yeah, I think I'm gonna fail systests. That's really bad. Unless this is somehow magically like okay, but I don't think it is. How many pretests were there? Oh, this is embarrassing. This is really bad. Because if I fail this, I'm also not even doing that well in the rest of my points. Oh, oh no, oh no. Oh no. Well, hopefully I pass these problems at least. But yeah, I think I'm gonna fail E, which is really embarrassing. Yeah, so all my code passed. D was definitely a little close, but you know, it passed on the samples. It passed pretest, so it's reasonable to expect it to pass systests. But yeah, I think this is the right thing I needed to do. I think this is what I should have done. Like for some reason I thought I only had to include one coordinate in the hash, but I actually need to include both. Actually, is that true? Oh, if I include only one coordinate, it's fine. Oh no, so my code will pass systests. Yeah, actually, yeah. So the reason is that even if this one coordinate occurs multiple times, they form disjoint. They form disjoint intervals. That's why this works. Sorry, I totally forgot about that. What happens is like you have these horizontal lines and you're decomposing these paths into horizontal lines and vertical lines. And so you only need one index to know which horizontal line it is. Or we're storing the depth. So strictly speaking, like the depth depends on both, but it really doesn't matter. So yeah, no. So what I originally had was actually correct. I will just revert my code back. That's a bit of a relief. Ooh, I really was scared there. Smart Andrew. Good. I am clearly smarter in contest than I am after the contest, so you know that's a good thing. So yeah, now I do think that this should pass. That makes a lot more sense why like it wasn't a problem. So yeah. Cool. Now I am running pass test 15, 23, 30. This is looking good. It's looking, at some point when you pass enough tests, it's like, so one thing that people try to do is upload, like, put the harder tests earlier. Sometimes people try and do this. And the reason is that, like, this way you kind of catch more bugs without having to run all the tests. And so at some point, if you get to like a pretty high number test, it's pretty likely that like your code will pass. At this point, they're kind of just stressing the edge cases. And especially if your code has like not too many edge cases, and like honestly a good litmus for that is just how many lines of code you have. Like so, then you should expect it to just work. So I did pass. I got really scared there for a minute. But yeah, I guess I might as well wait for systests to finish up entirely, and then I will call the stream, and I will, you know, call the stream. I don't know if they've put up the editorial already. Not yet. But yeah, that is a good game. We can go look at the status. And we can also check if there were any fails in our room. Looks like there were some fails on B. With TLE. Ooh. TLE on test 56. That's pretty rough. I wonder what their runtime was on the on samples. But yeah, I can't really tell if they yeah, it's hard to say. That code can be pretty complex, and especially pretty complex to like analyze the runtime of. I put in a bunch of heuristics and stuff to make sure that like to like try and check things earlier if I could. They obviously weren't all necessary, but you know, some of them were useful. So yeah, it looks like there's a lot of TLE on test 56, which is kind of, it's not really great. So one thing that people typically do expect from pretest is for them to contain like a max case, but perhaps they contain like a max case, but not a case that actually stresses the number of cliques that you have to test if you like try and do some particular optimizations. And so maybe that's why people are like close but not quite. So yeah, that is that's that. It looks like most of the the problems that are still running are problem B and C, because those are like the ones that take a long time to run. We can filter down to running to see how many are left. But it's only a couple percent. One other thing we can do while we're waiting, I guess, is we can go solve the div1 A and B. So I'll just do that really quickly. Given 4 integers, n, c0, c1, h, in a binary string of length n, you can change any character of s. You pay h coins. You want to buy the string, you should buy all its characters. Minimum number of coins needed to buy the string. Well, one thing to observe is that like every character is totally independent. Like the characters don't interact with each other. Like each character gets changed or not changed, and you pay or don't pay. And like the buying is the same. So really what you can do is you can say, like, if you start off with a 0, what are your options? You can either leave it as a 0, or you can buy it as a 1 and change it to or you can change it and then buy it as a 1. And likewise for type 1. So one way of actually doing this is you just start off by saying C0 is the min of C1 and C0 and C1 plus H, because you can either buy it immediately or you can swap it and buy it. And similarly, C1 equals min of C1 comma C0 plus H. You can actually just run both of these like in order, because like one of them will always be greater, and so you don't have to worry about like, you know, being able to like switch it twice or anything. Like if H were negative, then you would have some worries about like, you know, what if this means I bought it twice? But it's really not a big deal for this. So yeah, you can just run those two and then just add up the costs of buying the string as is. For problem B, the median is, do we define the median? Okay, given n over 2, so we want all the medians to be, we want the medians to have the maximum sum. And so, oops. And so, yeah, to maximize the median, the sum of the medians, pretty much we can like pick So pretty much the ith median has to be smaller than n over 2 numbers. It has to be smaller than n over 2 numbers, and it also has to be, so the ith median has to be smaller than itself. N over 2 numbers, it's smaller than a bunch of other medians, so it's smaller than the numbers that are bigger than those medians too. And so it's guaranteed to be in the bottom, like, it's guaranteed to be at most like 1 over like n over 2, like it's guaranteed to be at most the like n over 2 times ith biggest number. And so what you can do is you can just like, you can just take these and write them out this way. Like this is totally achievable, which is just like, you just put the numbers in this place and then you put the small numbers there. And so that's really how you do it. So you just divide all numbers. Pretty much you like take the biggest numbers, you put them all the way down until you hit the median. And then you take the next biggest numbers and you put them at the end of the next array. And pretty much like what you're trying to do is you're trying to like make the biggest median as big as possible, and then like not waste any of your other big numbers on that last array because we've already picked the median. So that's how you do this problem. But yeah, so sys testing is almost over, I think. There are last 2 problems that are running. But yeah, GG's. There were a lot of fails on B. Umnek also failed B. So unfortunately for him. But congrats to ITST and Raid. We can go look at rating changes. But I also have to run soon, so we will have to go to work soon. So we can take a look at that later. But yeah, looks like Nick has lost a bunch of rating because he failed. Raid gained a lot of rating, gained about 60 rating. And yeah, congrats to, I don't know if I see anyone who became LGM. So yeah, congrats to Idar for becoming LGM and Aristo for becoming LGM. So yeah, thank you guys for watching the stream, and well, I guess if I have time, I will really quickly just submit these two. I'll just code in here. I have a few minutes. All these numbers are small, so we don't have to worry about integer overflow or anything. I think that's a good thing for div2 problems, not to like force you to think about integer overflow, especially div2a. Like integer overflow is kind of just such a weird edge case that like you really don't want to be a barrier for people just getting into the contest. So yeah, we'll just do exactly what I said. You just run C0 equals min of C0 C1 plus H. C1 is min of C1 C0 plus H, and then you just add up the values of all the characters. So yeah, that is that one. Problem B. Let me see if I have to print out the table. Nope, we just have to print out the sum. Okay, so then it's a lot easier. Let me see if it's sorted or reverse sorted. The array is non-decreasing, so it's sorted. So I'll just reverse it. We don't have to bother. For I equals 0, I is less than I equals 1, I is less than n, I plus plus. No, this is actually n over 2 plus 1. So the number of things that are at least the median is n over 2 plus 1 because of how they define the median. So the median is the smaller of the two things, or it's the smaller of the two guys, or something else. So this is just n over 2 plus 1. And then, yeah. And we'll print out ends. I believe this is correct. Nope, not correct. Why is my number so big? I am probably doing some out of bounds. This is less than k. Is k the length of the array, or k arrays of size n? Okay. So yeah, good games. So thank you guys for watching, and I will see you guys next time.